The first truly open audio-video model.
It's out of this world. Check it out!
Welcome to Generative AI Futures. Every week, we peel back the layers on the technology that is just fundamentally reshaping how we all create.
And for the longest time, with AI video, we've seen these huge cinematic strides, photorealistic scenes, really complex motion.
But there was always this one major soul-crushing problem.
The silence.
Exactly, the silence. The videos were beautiful ghost ships. They were missing that vital soul of sound, you know, the character's emotion, the environmental foley, all the acoustics that ground a scene in reality. So our mission today is a deep dive into LTX-2. This is the new open source T2AV, that's text-to-audio-video foundation model.
From the engineers at LTX.
Right. And they set out to solve that silence by moving past what they call broken pipelines. Those are the old decoupled systems where you generate a video, then you try to bolt on some audio.
Or vice versa. It never feels right.
It never does. So the goal here is ambitious. We need to understand how they managed to model the joint distribution of sight and sound at the same time. What is the secret sauce for synchronizing video and audio with subframe precision?
That phrase you just used, broken pipelines, that's the whole insight driving this model. The decoupled approaches, they just fundamentally fail because they can't capture the bidirectional dependencies that exist in the real world.
Bidirectional. So sound affecting sight and sight affecting sound.
Exactly. Think about your acoustic environment. The visual context totally dictates the acoustics.
Yeah.
If a character claps their hands, the video needs to tell the audio stream if they're in, an echoey cave or a padded broadcast booth.
So reverberation, volume, that all comes from the visuals.
And it goes the other way, too. The audio, specifically speech, dictates crucial things like lip synchronization in the video. If sight and sound aren't influencing each other dynamically, continuously during generation, the whole thing just feels off, uncanny.
The uncanny valley.
LTX-2's whole innovation is building an architecture where sight and sound are in this constant real-time negotiation.
Okay, so let's unpack this. The model's DNA. The first thing that jumps out is that LTX-2 isn't, one huge expensive monolithic block. It uses an asymmetric dual-stream transformer.
Yes.
Why asymmetric? What's the thinking there?
It's purely about smart computational efficiency. It's about resource management. The whole model has 19 billion parameters, but they're not split evenly at all.
Okay.
The system dedicates a massive 14 billion parameters to the video stream, and that's non-negotiable, really. Video involves these complex, high-dimensional spatiotemporal dynamics. You've got motion, layout, color, frame consistency. It's a huge task.
And the audio?
The audio stream, by contrast, gets just 5 billion parameters. And that's because audio is inherently a 1D temporal sequence. It's just fundamentally less dense than 3D video data.
So it's a clever design choice. Put the horsepower where the complexity is on the visuals and let the audio stream be more nimble and efficient.
Exactly. It's specialized.
That specialization is fascinating. Okay, let's talk inputs. Before the transformer even starts, the model gets these latent compressed representations, and they're still modality specific. They use separate VAEs to compress the video and audio, specifically causal VAEs.
Right.
Why is that causal distinction important?
That's a crucial detail for any time series data. A standard VAE just compresses things. But a causal VAE makes sure that when it's compressing, say, the audio, the model can only look backward in time.
So it maintains the temporal order.
It guarantees the model understands the sequence of events. For sound, which is purely temporal, you have to maintain that causal forward-moving flow. It's essential.
Right. And decoupling these latents, keeping the video compressed separately from the audio, that allows for independent optimization, right? I mean, video gets encoded into 3D latents, X, Y, and time. Audio is just 1D latents from stereo MELS spectrograms. And beyond the efficiency, keeping them separate must have huge utility for creators. If you want to generate new video for existing audio, or the other way around, this architecture just inherently supports that.
Exactly right. It opens up creative doors a monolithic model just couldn't. But utility aside, to get really high-quality output, especially coherent speech, the model needs to be deeply fundamentally grounded in the text prompt.
Okay.
LTX-2 needed a text understanding that went way beyond the basic prompt embedding we saw in early models. If you're generating a person speaking, you need phonetic accuracy, not just, a person is talking.
The how, not just the what.
Precisely. So they chose the Gemma 312B multilingual text encoder as the backbone. That choice alone signals they're aiming for high-fidelity multilingual performance.
And this leads us to their first major innovation in conditioning, the multi-layer feature extractor. Standard practice is often just taking the final output layer of the LLM. Why pull features from all the decoder layers?
Because the final layer only gives you that high-level semantic meaning, the what. But for a complex generative task, you need the how. By extracting features across all the layers, they capture the entire hierarchy.
The whole hierarchy.
Yes. The early layers capture the raw, phonetic detail, the syntax, the actual sound of the language. The later layers capture the complex, abstract meaning.
So you get everything from phonemes to philosophy, basically.
A bit of an exaggeration, but yes. And these different features are then projected into a unified embedding space. It provides a significantly richer hierarchical conditioning signal.
Now here's the clever bit, and frankly the part that sounds a little like sci-fi. They introduce thinking tokens. If the multi-layer extractor is giving the model this deep understanding, what do these thinking tokens do on top of that?
They are exactly what they sound like. They're tokens designed to think. They are learnable, non-textual tokens. They get appended to the input sequence inside a component called the text connector module. They're not part of your original prompt.
So, wait, they're like little AI analysts that read the full prompt embedding and then generate their own meta summary before the main generation even kicks off.
That's a perfect way to frame it. They get processed using full bidirectional attention, which is different from the causal attention of the language model, and this happens before they condition the video and audio networks.
So they act as global information carriers.
Exactly, aggregating the complete context, enriching the representation. The so what here is that they overcome the limitations of Gemma 3's original causal attention. They make sure that when you write a really complex prompt, the model actually adheres to all the instructions, including the phonetic requirements for speech.
Okay, so we have two highly specialized streams, 14 million parameters for sight, 5 billion for sound, fueled by a deeply conditioned text signal. Now, the central challenge, how does this asymmetric architecture actually sync? This is where the mathematical rubber meets the road. It has to be that bidirectional handshake, the audio-visual cross-attention.
That is the absolute heart of the synchronization mechanism. They weave these cross-attention layers throughout the model's depth. It ensures a continuous flow of information in both directions, video to audio and audio to video.
V2A and A2V.
Right. This continuous feedback is how they capture dependencies, like a moving shadow affecting volume, or making sure the sound of water actually follows the visual of the water.
But cross-attention alone doesn't guarantee subframe precision. That has to come down to positional alignment, specifically how they use those rotary positional embeddings, or ROPE.
And this, to me, is the most elegant technical solution in the entire paper. During that cross-modal attention, the moment the video stream talks to the audio stream, or vice versa, the model uses only the 1D temporal component of ROPE for the queries and keys.
So they drop the spatial coordinates, the X and Y.
They intentionally drop them. It's a brilliant constraint. It forces the alignment strictly onto the shared time axis, the T. The model is essentially ignoring where an object is in space for that split second.
And focusing only on when it happens.
Exactly. It simplifies the synchronization problem immensely.
So they're telling the massive 14 billion parameter video stream, I don't care where the car is right now, just when its wheel hits the pothole, so the 5 billion parameter audio stream can make the thump at the exact right millisecond.
That's a perfect analogy.
Okay, timing is locked down. But now there's the scale problem. A huge 14B model talking to a 5B model. How do you make sure this large video orchestra and the smaller audio section finish the measure at the exact same time? Is that where cross-modality ADL-N comes in?
It is the conductor. ADL-N adaptive layer normalization. Its gates are conditioned on the hidden states of the other modality.
Ah.
This mechanism regulates the integration of cross-modal information at each denoising step. It helps maintain the flow and ensures that, despite the huge capacity difference, the audio and video features are synchronized in their diffusion time steps.
So one stream can't run ahead of the other.
It keeps them locked together. And you can see the proof in the paper's figure 3. It shows the model's mind at work.
Retention maps.
For environmental sounds, the video stream automatically attends to the car's visual position, tracking it for Foley. But for speech, the attention dynamically shifts between two speakers if they're talking, and when one person speaks, the focus locks right onto the lip region.
It's definitive proof that this continuous bidirectional lock is actually working.
The output quality and sync are clearly high, but the truly shocking part of this architecture is the inference speed and the control it gives you.
Okay, let's talk control. They use an extension of classifier-free guidance, CFG, called modality-aware CFG.
Right.
CFG is usually the one knob you turn to tell the model, hey, be more faithful to the prompt, but LTX-2 gives you two knobs.
Two independent scales.
Yeah.
You have C dollars, which is the traditional textual guidance strength, how closely do you follow the text. But then you have C ballers, which is the new cross-modal guidance strength.
Okay, so what does that mean in practice?
It gives you incredible power. Let's say your output looks great, but the lip sync is a tiny bit off. You don't have to change the prompt and regenerate everything. You could just turn up the cross-modal guidance at that cinema value to force tighter synchronization without necessarily altering your textual adherence, ST dollars. You can tune alignment independently of the prompt's meaning.
That is a massive leap in controllability. That's amazing. Okay, now the performance shock. You compared LTX-2, which is doing audio and video, to a leading video-only model.
2.214B, yeah.
And the numbers are frankly wild. LTX-2 with 19 billion parameters is about 18 times faster than 2.2, which is only 14 billion on an H100 GPU.
It's 1.22 seconds per diffusion step versus 22.0.
That's not an iteration, that's a whole paradigm shift. Is that extreme speed purely from the asymmetric architecture?
It is the primary reason. By dedicating only 5 billion parameters to the less complex audio task, you just dramatically reduce the computational burden. That specialized efficiency pays huge dividends in speed.
It makes real-time high-fidelity T2AV a sudden reality.
And that speed is what lets them generate high resolutions. Trying to generate full HD 1080p with a 14 billion parameter video model would normally choke even an H100 because of memory limits.
So how do you get around that? The multi-scale, multi-tile inference strategy?
Yes, and it's critical for quality. It's a three-step process. First, base generation at a lower resolution to get the scene and the sync perfect.
Okay.
Second, a latent upscaler to increase the spatial resolution. But here's the clever bit. The third step is tiled refinement.
It breaks it into smaller pieces.
Exactly. It splits the upscaled latents into smaller, overlapping tiles. These tiles get refined independently, allowing the model to synthesize intricate details like skin texture or fine hair without needing all 14 billion parameters to process the whole high-res image at once. Then it just blends them back together.
So what does this all mean for us, for you listening? LTX-2 is now the premier open-source T2AV model. It's setting new benchmarks for both quality and speed. We're talking about generating up to 20 seconds of continuous synchronized content,
which actually exceeds the current temporal limits of proprietary models like VO or Sora.
It's a huge deal.
The impact is significant. It democratizes high-quality audiovisual content creation. But of course, there are limits. Performance varies across languages, especially underrepresented ones. It can get confused with multiple speakers, and that 20-second limit isn't random temporal drift can start to happen.
And it's still just a generative model, no explicit reasoning.
Right.
Ultimately, the core idea you should walk away with is this. LTX-2 proves that in generative AI, just like in reality, perception is fundamentally multimodal. We've seen exactly how they achieve that crucial sync by forcing that cross-modal handshake to focus only on the shared time axis.
That 1D ropey constraint.
It's just a mathematically elegant solution to a massive engineering problem.
And this raises an interesting question for you to think about. Since the LTX-2 architecture separates the 1D temporal audio from the 3D spatiotemporal video, and it gives you that modality-aware guidance term, Taktabavdanar. What new forms of creative control could emerge if you could selectively apply that guidance only to specific time segments of the video, instead of across the whole clip?
So you could, fix just 1 second of bad lip sync?
Imagine running a diagnosis and fixing just one brief moment without having to alter or re-roll the other 15 seconds of your generation. What would that unlock?